Picture this. The cloud is down. The world's gone dark. And the only artificial intelligence you can trust is the one humming inside your own home. That stack of obsolete parts you shoved in a box. Today, we're turning them into a sovereign AI warhorse. We get it. Almost everywhere you look, AI is a new buzzword. Most coverage is doom and gloom, or convoluted at best. This project started with a desire to see if an unconventional approach could actually produce something realistically helpful that people would also enjoy using, while keeping all the data local and off the cloud. We're going to cover what hardware we used, limited to what we had on hand, the software stack, and also some particular large language models that we feel are well suited for folks who also have the mindset of self-reliance and preparedness. Keep in mind that this is not a deep dive. It is intended to provide some exposure on what is possible and some examples of implementation. Don't be mistaken. We aren't advocating for a replacement of human learned knowledge and experience. We see this technology as a force multiplier, an additional tool, and it is important to hold it in such regard. It is not, in any form, to be considered an all-knowing oracle. Let's dive in. This hardware is all stuff that we had laying around from years of tinkering, including a stint in the Ethereum mining world. We realize not everyone has stuff like this laying around, but right now, old mining hardware and other legacy hardware options are still ripe and good deals can be found. The bottom line is, despite what you might hear, you don't need pre-mill hardware to run game-changing large language models. For this build, we're using an old Zotac B150 mining motherboard with an Intel 7th Gen i3 CPU with integrated graphics, 16 gigs of DDR4, a 750-watt power supply, mining GPU risers, and 4 GPUs, an RTX 3070, two 3060 Ti's, and a Quadro RTX 4000, all with 8 gigs of VRAM. When using multiple, smaller VRAM GPUs, accommodation has to be made for the way the model layers get sliced and managed, so you'll probably need to plan for more VRAM than if you were using one single high VRAM GPU. We assembled the whole thing in an open-air mining rig. From here, install a recent flavor of Ubuntu. In our case, we opted for 22.04.5 desktop. But whether you're running Ubuntu 22 or 24, you should be good. Just download your operating system ISO file, burn your installer USB, we used Rufus on our Windows PC for that, and configure your installation. This probably means accessing the BIOS for your project's motherboard. As an example, here is a short clip of what the B150 BIOS looks like. Well, it's a BIOS, but there are some unique things about a mining board. There isn't a lot of documentation, but we decided to leave mining mode on. In theory, this should help the compute share across multiple GPUs. We also changed the PCIe lane settings to auto-determine the lane speed. We ran into some stability issues with it set to 3, but we found no noticeable performance change with it set to auto. Finally, make sure the system is set to boot from USB. That will kick off the Ubuntu installer. Work through the installer. We kept it simple, as we will be installing everything we need to manually. And once that's done, plug in and access the terminal. Everybody's favorite place, and this is where the real work starts. First up is updating the system. So, sudo apt update. After that runs through, I'm going to install some packages that we'll need and will make our life easier. Sudo apt install -h and a bunch of different packages. Depending on how you configured your Ubuntu install, some of these may already be present. Once that's done, I'm going to jot down the IP address so I can use PuTTY for my Windows machine. But everything I do in PuTTY can also be done on the local terminal. PuTTY is just an easy way to remote into the Linux system from Windows using Secure Shell. Now that we're connected, we can get into the real meat and potatoes. First up, we're going to install our NVIDIA GPU drivers. This will run through and install what the system thinks is the best fit. In reality, this should actually work out pretty well, but you can install specific drivers if needed. In this case though, we got what we needed and we finished and rebooted our system. The next part is a little more tricky. Once we putty back into the system, we're going to install the NVIDIA Container Toolkit. This string of commands configures our system to install the latest NVIDIA Container Toolkit. It looks a little complicated, but all these commands are listed in the video description along with some easier options such as this one-liner. There is also an even simpler option that usually works, but with the timing of this video, it looks like an NVIDIA signature may have been out of whack and have required a much more detailed command. But if you're doing a project like this, try the simple route first, and it may just work out for you. Once that's done, we can test it and see if it's working, but we don't have Docker installed yet. Let's fix that. A simple curl command gets us Docker. Once that installs, we can add Docker to our user so we don't have to sudo every Docker command. With that done, we'll reboot for a fresh session. With Docker installed, let's run a command to check and make sure everything is visible and working as expected. And boom, that's perfect. With the system set, let's make a new directory for our project. There we go. Make dir Ollama stack. And now let's change into that directory and mix the secret sauce with a Docker compose file. This is our Docker compose, and it has several important parts that really make this work. The first is, we're using Ollama version 0.6.6. Recent versions of Ollama have moved to a different type of model memory mapping engine, so we commented out that latest Ollama image version. We've also added the Ollama keep alive variable and set it to keep a model loaded indefinitely. This is really key for this server, and it cuts down on model load times. Once we use a model, it will stay loaded and ready to go. The next big thing is the context length. A little trial and error, and we settled on 24,000 as the optimal context length. In case you don't know, context is very important to the effective use of large language models. Very basic terms, a word is roughly equal to a token, and the context size dictates how many tokens from the conversation are used to compute the system's response. Historically, default context size for Ollama was about 2,000 tokens, and for casual use, this is usually okay. But if you're engaged in an especially long or large project, this can cause issues with the model forgetting key facts, such as if you're writing a long story or working on a coding project, or any sort of large text analysis. Let's save that Docker compose and bring it up. It's our first time, so the system needs to pull the Docker images. Once you have the images though, no feature pull is required unless you're updating the system. With the containers up, we can go ahead and log in. In the browser window, navigate to your server's IP address followed by the port specified in the Docker compose. In our case, that is port 3000. It's our first time logging in, so we have to create the admin account. Now, all of this information stays local. You can see this email address isn't real. And the first thing I like to do, since this is my own local server, is to allow new users and give them admin rights. You can set this however you prefer. If you don't trust admin level access for new users, that's fine. After that, we're going to navigate over to the Models section. Select the download icon, and here we can download available models. First up, I'm going to download Gemma 3 27B QAT. This model is optimized for quantization, providing more accurate responses with a lower RAM requirement. It's also multimodal, meaning it can use multiple forms of input to include pictures. With the model downloaded, I'm going to now download our second main model, MedGemma 27B. The cool thing here is that even though there isn't an official MedGemma Ollama release, with this URL from Hugging Face, we can still download the Unsloth GGUF Quaint 4 KM model. Depending on your needs, there are a ton of models on Hugging Face that could be used with Ollama in a similar manner. It's worth checking out if you have a niche use case. MedGemma is an excellent model, especially for those folks who have a self-reliance or preparedness mindset. It is basically Gemma 3, but it has been fine-tuned by Google on medical-specific data. This version loses the multimodal capability, which is why we downloaded the actual Gemma 3 27B version. But by being text only, it is very high performance for text inference, and in our testing we haven't noticed any deficits among non-medical areas. It really is a phenomenal model, and it's flying under a lot of radars. We also have NVIDIA SMI running in an adjacent window, so you can see how the model loads into the system. This is all real time, and it actually loads from zero relatively quickly given the architecture of the system that we have. Again, once the model is loaded, it will stay in VRAM, so follow-on chats will be near instantaneous. Once it loads, you can see the response comes in pretty fast, right around 16 tokens a second. And we can do follow-on prompts from the auto-generated options, and even that comes in pretty quickly. This is just the performance that we were looking for. A second example of a more medical-focused question. Here the model is already loaded into VRAM, so the response is again very fast. Checking out the other window, we can see how the model is loaded across the system resources, and that the model is set to stay loaded. As the response continues, you can see that even with a basic prompt like this, it is able to produce a pretty thorough response. I might be a little biased since I'm a former 18 Delta, but to me this would be an incredible resource to have on hand, and it's very similar to having another person available to gain an alternate perspective. Now, this isn't a replacement for experienced medical professionals, but if you've had some medical training, or the medical and emergency systems are degraded, this can help fill in some gaps. Okay, let's switch models. Here you can see MedGemma is still loaded, but it's going to dump that and load Gemma 3. It's going to go through the process and reload the model into the system resources. You can see the VRAM allocation looks a little different, and the speed of a response has dropped significantly. A more detailed look at the system resources, and it's apparent that part of the model is actually allocated to the CPU and RAM. This is what is slowing us down. So if you have a faster base system, your performance will be a little better. The problem here lies with our use of multiple 8GB GPUs and the multimodal aspects of the model. Even with the performance hit that we took, this model really shines when using its multimodal capabilities. For example, we can use it to translate a foreign language in an image file, not even a text file. This brings a whole new capability to the table for translation and analysis. With the model preloaded into the system, our response, while being a little slow, starts coming back almost instantly. Not too shabby. More complex translation and analysis is also possible. No cloud. We don't even need internet at this point. If you don't like the long naming convention that comes with the model downloads, we can easily navigate over to our models under the admin panel and edit the display name of our models. Just some basic housekeeping, but I think this is needed to create a slightly better user experience for my non-techie users. And to further improve the user experience, we can easily create an app-like experience to use the server when we are connected to the local network. For example, On an iPhone, if we have our Open Web UI open in the browser, select this icon. Then select Add to Home Screen. Name your icon whatever you want, and hit Add. Boom! A makeshift app for easy access, and a similar process works for Android as well. With the server now up and running, one thing no doubt on a lot of people's mind is the question of energy efficiency. So, we plug the system into a kilowatt to get a good idea of the actual whole system power draw. And here we have the system idle draw while it is sitting waiting for a user prompt. And now, under full compute. In my opinion, this really isn't too bad, considering we have 4 GPUs and what we're running. We haven't even tweaked the system power settings. We could get this number down even more if we really wanted to, and we probably will play around with this in the future. Finally, we have the server installed in its new home, in a makeshift rack along with the UPS. Ultimately, we were extremely pleased with the outcome of this project and its real-life usefulness over testing the last few weeks. So there you have it. By no means do you need the latest gear to run a beefy large language model with extended context at good tokens per second speeds. It's also very easy to create a very cloud-like service user experience, helping to make sure users actually want to use the system and everyone's data stays local with all the benefits of multimodal inference. Properly built and utilized, these systems are some of the best persistent force multipliers we've seen, and are still continuing to evolve. Let us know your thoughts, good, bad, or indifferent, and continue improving your figurative fighting position. Until next time.